Again, I'm Michael Barker. I'm actually a professor of civil and architectural engineering at the University of Wyoming, but I'm also the director of education for the Short Span Steel Bridge Alliance. And our my topics are pretty simple today. This is a little lower key than we've had. I mean, Mike Kulmo did a great job with the integral abutments, and Brian Hartnagel did a great job with that innovative, simple for dead, continuous for live. We're going to back up and just talk about our typical bridges today. And we're going to start off by talking about some design resources for short span steel bridges. As Marissa mentioned, we have something called E-span and E-beam 140 design software. And then we do want to talk about if you have a bridge need, you can talk to one of the bridge manufacturers and just have them deliver you a bridge, a prefabricated bridge. We're going to look at a couple case studies for that. So our job as bridge engineers or owners or whatever, municipality engineers, is that we have an opening we got to cross. We need a bridge. We're going to start by talking about traditionally fabricated steel bridges where it goes either design bid build or design build, where for this example, we need an 80-foot simple span bridge that's 2 lanes wide to cross this creek. And that's kind of where we start when we talk about bridge design. And somebody comes up with, it's either the owner or the engineer or planning commissions or whatever, they say, all right, we need that 80-foot simple span bridge, and we're going to make a composite steel girder bridge because we need this hydraulic opening and this clearances and all that kind of stuff. And we need 2 travel lanes because it's kind of a rural road, but it's a busy road. We have an average daily traffic of 5,600 in one direction. And we like our roadway width to be 34 feet, so we have a couple shoulders, one on each side, and we like these jersey barriers at the end. And that's kind of the service part of this bridge. This is what the traveling public needs. This is what they see. And as the engineer, we got to decide what goes in under this. We need an initial design for the bridge superstructure, how we're going to hold up this service part of this bridge. And the Short Span Steel Bridge Alliance many years ago developed what's called E-span 140, which are standard designs for short span steel bridges. It does both W shapes and plate girder bridges up from spans from 20 feet up to 140 feet in 5-foot increments for 4 different girder spacings. But for each design it spits out, it'll give you the steel girders, the shear stud and stiffener layouts, the welding and fabrication details, even the bearings and concrete deck design. And I just have some pictures here to show you some typical details that it's going to put out when you ask it, what is a solution for this 80-foot span? And this is what E-span covers. You can see the green bars is what types of bridges on the left side it's going to give you solutions for the length of bridge you have. And we're looking at that 80 foot. So it's going to give us a rolled beam bridge and it's going to give us a plate girder bridge. It's also going to give us recommendations from our bridge manufacturers for a press brake tub girder bridge or a buried steel bridge. And I'm going to talk about those a little bit later, but we're going to look up at those first two, our typical girder type bridge. And when we go into that, it's really simple. On the left, we put in how long it is. On the right, we put in how many traffic lanes there are. What roadway width do we want? What's that parapet width? And what kind of deck overhangs do we like? And that's kind of it. Because then it's going to apply all the Astro codes. Now, it's not Astro 10 yet. It's Astro 9th edition, but it's going to look at all the different combinations and it's going to try to minimize the girded lines and that kind of thing. So here's what it gives us for the rolled beam section. It says, hey, how about if we look at 4 girders at 10-foot 6-inch spacings, 20-foot diaphragm spacings, and if we do that, a W36 by 210 is the rolled beam that should work. Now this is preliminary design and it gives us a good starting point, but this should work. If we move on to the plate girder, this is a plate girder design. It also says 4 girders at 10-foot 6-inch. That fits the spacing well. Also 20-foot diaphragm spacings. But now we're going to decrease the amount of steel or optimize that section as a composite bridge, which means the top flange smaller than the bottom flange. And then we're going to have a larger bottom flange out in the middle where our moments are highest. And we're going to transition that to a smaller flange at the ends. And our top flange comes out to be 16 by 1. And bottom flange, it starts with that, but then it goes out to a 16 by 1.5 for 48 feet, and then it goes back. And this is going to save steel material compared to that rolled shape. But of course, there's also the fabrication part of this. And so we want to consider both, and it gives us both solutions, and now we can move forward. And that's what eSpan does. eSpan 140 gives us a preliminary design that says, this is close to what should work. And what it told us was 4 girders at 10'6", and it's got the deck up there, and there's our elevation of our girder. And now we can go into a final design type process. That's been around for, oh, I don't know, 15 years now or something like that, 14 years. And it's being used all over the place in counties and states, and municipal engineers really appreciate the ability to be able to get that trial design in just a couple minutes so that they can lay it to other types of materials and then look at what is their best value. But the Alliance back in 2025 released something new. And you can tell I switched from green border to blue border because this is brand new, and we think this is really important for our small consulting firms, our county engineers, our state engineers, whoever is looking at designing a simple span steel bridge. So this is an Excel program that will design non-composite and composite simple span rolled section steel bridges. And there's a disclaimer here, but what I do is I encourage you to go to the website there, or just the regular website, and then go there to look at this to see if you think this can be helpful. And I'm going to pretend like we're doing a demonstration here. I'm going to look at a non-composite bridge, 52-foot long, 2 12-foot lanes. I can pick the girder spacing, so I pick 6 girders at 5'6". You know, a typical county type bridge with 1'3" overhangs, some barriers, a roadway width, a bridge width, diaphragms. I only have one diaphragm right at the middle, so there's 2 unbraced lengths here, and I am going to consider it to be an unbraced because I'm using a corrugated metal deck and gravel riding surface. And I'm going to assume that that corrugated metal deck's not attached to the girders to give them the lateral support. And then there's some other stuff I do here that's not all that important. I do have a average daily truck traffic in a single lane of 200. That tells us what our fatigue requirements are. And I don't have any user-defined vehicles. We're just using the AASHTO HL93 loading. And it's at this point, if all my talk was on E-beam 140, I would go into that Excel program and actually demonstrate it. And I don't have time to do that today, but we can talk about it. And then there is a video on the website where I go through step by step and use that program to show engineers or owners how to input a bridge. But it's a really flexible program, and it is near optimized. It is Excel based, and it can do non-composite or composite. You can look at 5 different yield stress steels. Now, we didn't have the 33 or the 36 in there in the beginning, but we have a lot of counties that through a state program have old beams coming out of state bridges that they want to put into county bridges, and they don't know how to design for those lower yield stresses. Well, now they have a program that can. So we added the 33 and the 36, and the future is 65. It's here, but not real common. And then, of course, 70 is that upper limit right now. But it's so flexible with bridge layout and diaphragm variations along the span. So you can even do skewed bridges with this thing. And you can put on any decking. If it's non-composite, it can be wood, a grid, corrugated metal decking with gravel, a non-composite concrete deck, or a composite concrete deck. And like I said, it does the HL93 Astro loading. And something that not very many programs do, you can also define your own vehicle like a logging truck. I said the diaphragm is variable along the span. You can have up to 7 unbraced lengths, so you can do skewed bridges. You can determine whether the compression flange is braced during construction and braced during the final state. We've began by saying it's unbraced here. You can have any decking, like I said. If it is a composite, which I will show a little bit of that, if it is composite, it's got the F prime C. Is it full depth or does it have stay in place forms? Is there a haunch? Is there a sacrificial surface? And how do we do the shear connector design? And it does all of that. And it also has a lot of flexibility that we can put on utility loads or additional dead loads and variable bridge railings. And then the steel beam weights are individually considered in each design. It's not just assumed to be heavy. We can put a wearing surface on there. And then the vehicular loading. Yes, it does the Astro HL93 truck. Tandem and lane, but it also does a defined vehicle, like a logging truck, like a U80 truck. And here's where it has additional flexibility because many people would consider that a strength 2 with a lower live load factor. And so we can do that. We may or may not want to put an optional lane load with that state specified or county specified vehicle. We can say, hey, that truck is so big, it's only going to be on the bridge by itself. So we use single lane distribution factors, or we can use multiple lane, and we can even change the impact factor for those. And then, of course, it does a line girder analysis, which it means it estimates the total dead wearing surface live loads on a single girder and designs that girder. And for the vehicular loadings, it uses live load distribution factors, where it considers all the different factors for all the different types of bridge decks because they change, in addition to the original rotational stuff in AASHTO. Or you can put in your own live load distribution factors if you want. And then here's where it starts narrowing down the solutions. And we can control that. We can say, hey, we want a maximum L over D of 30. We can say we want a minimum depth of 18 inches because we know what type of diaphragms we like putting in there. We need a maximum depth of 33 inches because we don't want to do a lot of approach work. That's expensive, or we have clearance issues. We have those W40 and W44 rolled shapes, but they only come from one producer. And so there's usually kind of a price premium on there. And we can just say, yeah, we do want to consider them or we don't. We can put in our own deflection limits. We can put in our own percent, a little bit extra to take care of the diaphragms and stiffeners and things like that. And then it applies AASHTO. Now, AASHTO for the non-composite part has a couple different ways you can do that. There's the conservative approach, limiting stresses, or there's the more accurate optimum approach in Appendix A6, and the user can choose which one they want to use. And that's been changed in AASHTO 10. This product is AASHTO 10, the new LRFD bridge design specifications. And one of the things that changed that is quite significant is that moment adjustment CB factor for lateral torsional buckling. And it actually goes back to AISC, the building peoples now, or you can put in your own. It'll do fatigue 1 or fatigue 2 based on your average daily truck traffic in a single lane. And those requirements have changed in AASHTO 10. They've become better. You can do a variable design life. So what it does is it's going to perform dead construction and live load analysis for each unbraced length on your girder. And then it's going to do a strength 1 or strength 2 and constructability design check for each unbraced length. Of course, there's that service 2 check near the center line, maximum moment. And then we have fatigue, which we always have to be cognizant of. And it's going to check it at the critical location of a stiffener. And then if it's a composite bridge, it will do the strength and fatigue shear stud design for that bridge. And we're going to take a look at that now. So it's going to take all the information you give it as what this bridge is, the spacing, the lateral distribution factors, all that kind of stuff. And it's going to look at every W shape that is made and remember which ones meet the strength 1 and 2, service 2, and construction performance ratios. And then it's going to check the corresponding fatigue and the corresponding deflection. So for instance, here, this table here shows that for this bridge we put in, the W36 by 135 is the lightest. It also meets deflection, fatigue, and it also meets deflection, and it gives some more information there. If we wanted something shorter, like a W27 by 146, 2 down from that, yeah, that meets the strength, service 2 and construction, and the fatigue, but the deflection's not quite. It's at a deflection of L over 761, and our limit was L over 800. That's probably close enough. We could live with that if we wanted to go heavier but shorter because of approaches or clearance. But it gives us options here, whereas that E-span 140 doesn't quite get to that level. And then we can take a look at our bridge. We can say, we can investigate. We can say, what if we change the diaphragm spacing? What if we don't want the lightest weight solution? What if we wanted to check that W27 by 146? All we do is change that yellow boxer to W27 by 146, and it's going to give us all of the performance ratios for strength and service and construction, fatigue and deflection. And it's even going to go to each unbraced length and tell us the behavior in there so that we can become intimate with that bridge and start playing what if questions. And then, of course, there's a big design summary page where it gives us our nominal moments, but also all of the performance ratios or all of the design checks for our limit states, including strength and construction. And it also, right there at the bottom, gives us our abutment reactions, how much dead, wearing surface, and then how much live load abutment reactions and what are their eccentricities, because we have to design for that eccentricity in our abutment design. Okay, so that was the main demonstration. Not now I want to talk about that what if question. For instance, I only had one diaphragm right at the middle, and this is an unbraced. So I know lateral torsional buckling is probably the controlling design strength. What if I put in another bracing? Okay, let's look at that. And then we assume this is unbraced. What if our bridge manufacturer or our contractor attaches that corrugated metal deck so that now that flange is braced? What's that going to do? And of course, we did not put a user-defined vehicle on this. And so here, right up here, I'm saying I am going to put in one additional brace. So instead of two unbraced lengths of 26 feet each, I'm going to have 19, 14, and 19, which is going to improve my lateral torsional buckling capacity. And we see instead of a W36 by 135, it goes down to a W33 by 118. That's 5,400 pounds of steel I saved by playing this what if game. But of course, I do need that additional diaphragm. But I can do that in just a matter of moments. Or what if my contractor does attach with puddle welds or whatever that corrugated metal deck to the top flange of my steel beam so that that top flange is braced, or my L sub B is 0. I get down to a W30 by 116. That's 6,000 pounds of steel saved without even having to add another diaphragm. And so we can do all sorts of these what if games to try to come up with an economical, practical design. So this was a 52-foot simple span, corrugated metal deck with gravel as a riding surface, 6 girders at 5.5 feet. If I have a logging truck, now I didn't show a picture of the truck, but those logging trucks are big and heavy. They have 5 axles and they weigh 160,000 pounds. And I can just put that into this program and it's going to, and I tell it what live load factor, like here at the bottom, the bottom 2 lines here, I'm going to treat it like a strength 2 limit state, which means my live load factor is not 1.75, it's 1.35. No lane load. I'm going to use single lane distribution factors because on this rural type bridge, if that logging truck's going over, there's not going to be anybody else on that bridge. And I looked at unbraced and braced. The top one's unbraced, and I come up with a W36 by 150. Yeah, 15 pounds more per foot because that truck is big and heavy. Or if it's braced, 33 by 130, just a little bit more. Or actually less than the unbraced, but a little bit more than the braced. But what's cool here is this can be done with just a couple changes in cells in an Excel file. Okay, let's look at another short demonstration. Because I said this does composite and non-composite, so this is a composite bridge. I made it a little bit longer, 62-foot length. It's about the same, two 12-foot lengths, but since it's composite, I want a little wider girder spacing, so I'm going to look at 4 girders at 9-foot spacing. If I wanted to try some other spacing, it's easy. I just change it and rerun it. 2-foot overhang, barriers, roadway width. I'm going to have an 8-inch structural deck on top of a stay-in-place forms, SIP, which are 2 inches, and I have a 1/2-inch sacrificial surface on top of that 8-inch structural depth, and it's a 2-inch haunch from the top of the web. Okay, that's pretty detailed, but this program can handle all of that. And so I put in the weight for the stay-in-place forms, and I'm going to use 7/8-inch shear studs. And on the right side here, I am going to put a wearing surface on it, which is, of course, the DW load, but I have construction loads on this. When I form up and place that concrete on the overhangs, I have equipment out there and I have wet concrete out there that's going to be applied to the non-composite unbraced girder. And that's a pretty important AASHTO design check that's come into the code in the last 5 years or so, or 8 years. And I also have some other things I'm going to put on there. But now I'm going to give it quite a bit of average daily truck traffic in a single lane, so it becomes a infinite life fatigue 1 design check. And when I put that in there, and a minute later, it tells me W36 by 135, where fatigue was the controlling performance ratio. Now the 36 by 135 being the same as the non-composite, that's just a coincidence. But it's going to do the same thing. It's going to give me the top ones from lightest to heavier that meet the strength, service to, and construction, check whether it meets fatigue, and then check whether it meets deflection. And I can do the same rationale here. I can say, okay, my lightest is a 36-inch beam. That's going to make me increase my approaches. I can save 3 inches by adding 6 pounds per foot on the steel. That might save me a whole bunch of money on approaches. And I can do all that with the what if sheet in this Excel. I can just put in that W33 by 141 here and look at what happens. And of course, we see on that one that construction's got a performance ratio of 95%. That's right. Construction can control design. And so sometimes we want to start there to make sure construction does not become a problem. And then here's just the results page again. It's going to give us all the input information, all the lateral load distribution factors, all the different girder moments and stuff like that, and do all the design checks. It'll go through the strength by unbraced length by unbraced length, the construction, and it also gives us dead load deflections, whether it's composite or non-composite, so that we can plan for our cambers. Also gives us those abutment reactions that are very useful when we start talking about what are we going to put at the ends. But since it's a composite bridge, it's also going to give us options on adequate shear stud spacings that meet AASHTO 10. And AASHTO 10 changed quite a bit. It's gotten a lot better, a lot more economical. And so it'll give us the whole design that's pretty much optimized for what we have input. So to wrap up this topic, okay, we have that. We have E-beam 140, rolled shape, bridge design, composite and non-composite. On the website that you see there, you can see a user manual, you can see a couple examples, you can see a video of going through the Excel file. And I don't know how many have been downloaded, but it's being used all over the country. The county engineers love it because they can get an optimized design on the table in just a matter of a few minutes. And so with that success, we wanted to take it another step. And we're doing a plate girder one that's going to be released here in 2026. Because what we're looking at is at the 70-foot, 80-foot, 90-foot ranges, that our efficient fabricators can many times make plate girders, even though there's the fabrication costs, for less money than the heavier W shapes that have to be put in there because they're doubly symmetric. And so we developed this. It is developed, it just hasn't been reviewed yet. Very similar. Only now, of course, if you've got a plate girder bridge, there's an infinite number of possible solutions. And so to narrow that down, what the user does is they start at the top right here and they say, hey, I want a target span over depth ratio of 25. And then the program's going to go that -2 inches, use that +2, +4, +6. So 5 different web depths. And then it goes through a whole bunch of different flanges for the top and flanges for the bottom, to where it's going to look at 5,100 possible design combinations. And then it's going to create this bottom right table. There's also the shorter one like we saw with the E-beam, but here's one where from lightest down to heavier ones that all make the design requirements according to AASHTO 10. But with those infinite number of possible solutions, now we have to be engineers and we have to say, okay, I'm going to come in here. And in the yellow, I say, I want to try a 13 by 3/4 inch top flange, a 38 by a 1/2 inch web, a 17 by 3/4 inch bottom flange. And it's going to give us that solution and the performance ratios and what happens within the unbraced lengths. It's going to check all the AASHTO requirements. And then, oops, I lost a page here. And then it's going to give you a solutions page, just like it did for the rolled shapes, where it says, hey, this is what you selected. Here are the results. You verify this. You sign the drawings. You have just designed a well, this one's composite, a composite plate girder bridge in a matter of just a couple minutes. So look for that in 2026. It is developed. It's under review and doing a few upgrades to it. But this could be another possible game changer for those counties that have 70, 80, 90-foot simple spans to get over these crossings. Okay, so that we started by saying we have a traditionally fabricated bridge where we're going to design it, order it, whether it's design, bid, build, or design, build. What can our manufacturing companies do? I still need a bridge, like it says here at the top, but there are companies out there, alliance members, and you can go to the website and find out who all of these members are, that will take your requirements, design, sign, and deliver that bridge to you, to where either your county can put it in, your county forces can put it in, or a contractor can put it in. And of course, we deal with trusses and modular rolled shapes and even some accelerated bridge construction abutments, like down there at the bottom middle, or maybe that buried steel bridge up at the top right. And I'm going to look at the modular beam bridges. Now, my little box here in the green says, yeah, there are other types of prefabricated bridges that include buried steel bridges culverts, buried steel bridges arches. I talked about those a year ago at a Minnesota LTAP webinar online. Trusses and press brake tub girders. So I'm kind of leaving that for going backwards if you're interested in those, because the most common prefabricated bridge that our companies put out there are modular beam bridges, where they put a couple of girders together and already have the diaphragms, and maybe even have the deck attached to it that we can just lift into place, connect together, and you have a bridge. And they're economical. They go together well because this is what they do. The shop quality is high because of economies of scale. They're building these things all the time, and they're shipped as modules, and they're lifted in place, and you can have all different kinds of riding surfaces. And I'm going to look at two of them, two that I think are interesting. The first one, one reason I think this is interesting is that a county crew built this bridge in just a day. Now, it took a little longer to get the new abutments in place and stuff like that. But when the bridge came, it took them a day to put it into place. So the fabricator was Big R, which recently got bought out by Contech Engineered Solutions. The contractor, Whitman County, Washington, used their county crew, the same people that mow and drive snow plows and work on everything else, build their bridges. And the design engineer was actually their county engineer, Mark Story. And so I've got a picture there of the old bridge, right? The old bridge is a wood bridge. Yeah, it's deteriorating, it's old. And when we put in a new bridge, first thing we say is, can we use the old abutments? No, those are wood. They need to be replaced. And of course, we're probably going to want to increase the hydraulic opening by making it longer and maybe even raising the bottom of it to get flood clearance. And that's what they did with this. Now, the way Washington, Whitman County does it is they drive piles and just put a cap on top for their abutment and then a back wall. But they ordered this bridge and it came on one truck, as you can see on the top right. And then you can use pretty light equipment. There's this county owned equipment to lift those off and put them in place, as you can see towards the middle bottom. So the new bridge was 35-foot span. I forget what the old one was, 28-foot wide, so a little wider. Two girder modules. There were three modules that came on this truck. They were fully assembled, and even with a corrugated steel deck on there and simple connections, they put them into place. They take them off the truck. They put them into place. They connect them together with just bolts. They put a back wall there because of their simple abutment, and they push gravel on there and they have a road in one day. Now, when they built this one, I'm not talking much about costs, but here's one. It took them 4 weeks from beginning to end. One day to put the bridge in, but of course, getting it ready took a little longer and waiting for the delivery. But they bid it both steel and concrete. Steel came in at 59,000. The concrete came in at 82. They let and then the other cost would be about the same for the two bridges, and they let the market decide that they're going to build a steel bridge here. Here's the other one, and again, another modular beam, but this one's a contractor built one, right? The owner said, hey, design it. Asked, again, this is a Big R contact one, design it, sign it, deliver it to us, and I'm going to have a contractor put in the foundations and build the bridge. And the contractor was Quality Excavation, and the design engineer was Pacific Forest Resources. But that bottom right picture, we see those all over. Now, this is in National Forest type area, and we see those all over. And of course, that's not good. I'm a big fisherman, and I hate seeing something like that because that's a barrier to fish movement, and it restricts the stream, and it's got all sorts of environmental issues. And so we see a lot of these being replaced by span type bridges. And again, we want to increase the hydraulic opening. We're going to have, for this case, they said they needed a 55 or 60-foot span to do that. But this is out in the middle of nowhere, floodplain, that kind of thing, and they had some poor soils. And this is out in the middle of nowhere. And so large equipment would be really difficult. And because it's a forest, they needed special logging vehicle. So I said there were poor soils. It was just on the right end. And that's the reason, that's one reason I'm showing this example is they used a steel bin abutment, which I thought was pretty neat. And since that was there as the abutment, they could go down to a 50-foot span because of the vertical vertical profile on one end. And they could use this smaller steel bin abutment because steel is a light superstructure. Okay, and this is going to be a corrugated metal deck again, and it's going to have gravel. But they could only get in a couple excavators in this real tight area. They could not get cranes in there or anything like that. And so they use this modular superstructure and this box bin to put this bridge into this sensitive area. So you can see that picture on the bottom right, or the picture above it too, is a schematic, but the steel box is just that. You put a steel box in and you put gravel and geosynthetic layer and gravel and geosynthetic layer to form a very strong abutment. Then you put a little cap on top of that for your a pier or your abutment, and you put the bearings on top of that. The left abutment was better soiled. I just needed a precast sill. And then both were, of course, protected with riprap because of the flooding characteristics of this region. And I just want to show some pictures of them building that bin, right? Top left picture, hey, you dig a hole. Middle picture, top, you build it. To the right, you start filling it and putting in the gravel layers with the geosynthetics in between. I forget what they were, 16-inch layers if I remember right. Put a sill on the top with the bottom left picture, and all of a sudden you've got a strong abutment that did not take big equipment, did not take concrete pours to do out in the middle of nowhere. Now the superstructure is pretty much like the last one I showed. You know, because of they wanted a steel structure because of the weight, because they didn't want a huge abutment there, and handling and convenience and the modular design. So this came out in 2 girder modules, again, so fully assembled and with simple connections, and then it came in on one truck. They pick it up with light equipment, they place it on the bridge, they push the gravel on top, put a back wall in and that kind of stuff. And then they push the gravel on it, and they have a long-lasting, aesthetically pleasing bridge out in the middle of nowhere. And then again, I did show this. 2 weeks it took them for not only putting the bridge goes in one day, but the excavation, the stream restoration, the box beam installation, that kind of stuff. They put this thing in 2 weeks for a cost of almost $204 per square foot. A little expensive because, of course, you can imagine those box beam abutments or steel box abutments, they cost something. And so that raised this price just a little bit. Now, there are other modular beams out there, and the reason I'm showing this slide is because of Wheeler. Wheeler is in Minneapolis, Minnesota, and they are building bridges, modular bridges that they send out all over the country. And the reason I'm showing these two is on the left side, you have a concrete decked modular beam accelerated bridge construction project where in Axtell, Utah, that old bridge was, they were closing it. And there's a lot of ranches and farms that needed to get their stuff across that road. And so they built that modular bridge, second picture to the right, with a, you know, it's a certain level, a bridge rail and all that kind of stuff in a quick time. And I showed that because that's the first two I did were gravel decks. This is a concrete deck. On the right, there was this big weather event that literally wiped out a bridge in Wisconsin several years back. And this is in the middle of winter. I know you don't see a lot of snow there, but this was during really cold temperatures, and it literally cut off communities. And so Wheeler came in on that bottom right and said, hey, we can build a modular steel beam bridge with a wood deck, asphalt overlay, crash tested barriers, and steel and wood abutments. And we don't have to cast any concrete, and we can get this thing built really, really quickly. No concrete curing time, no concrete temperature issues. And so I just wanted to show these. one, Wheeler, is in Minneapolis, and this is Minnesota LTAP, and the concrete and the wood deck systems. Okay, I'm getting close to done, but I thought I'd just, now it's my marketing time, right? We should consider short span steel bridges for any crossing. We have so many case studies that show they're economical. We have so many case studies that show that they can go in with less construction, less disruption, and things like that. So I thought I'd just kind of summarize a few things here that, yes, short span steel bridges are cost effective because we have simple and practical details. None of this fancy X bracing and K bracing and all these complicated details. Simple span bridges are simple, so we have simple and practical details, which can be put in with lighter equipment and require smaller abutments because of its weight. Speed of construction, if you want to put a bridge in a day, you can do it. No problem. You can do accelerated bridge construction. You can do modular construction. You can even have traditionally fabricated bridges modularized in the fabrication shop so you can do the modular construction. Longevity. We didn't talk much about this, but the new goal for a bridge is more than 100 years. Yes, it used to be 50. Currently, or just in the recent past, it was 75. Now we want to go to 100. There are thousands of 100-year-old plus bridges, steel bridges out there that are still functioning well because of durable materials, corrosion protection systems, and with our new design, practical design things where we try to get rid of joints so we don't get leaking to the steel. And we have integral abutments like we saw a couple lectures ago here. We can get these bridges to go past 100 years, no problem. And the last thing, resilient and sustainable. We know that's important in today's world, that we want, as a goal, the intersection here. We want a resilient and a sustainable steel bridge that lasts 100 plus years. And we've got it. On the left side, I kind of put what I think of resiliency, that we can inspect it. And if there is something that goes wrong, we can repair it. It's a highly redundant system for moment or force redistributions. It's flexible in the design. It's adaptable. Its resistance to hazards is very strong, whether it's earthquakes or floods or hurricanes or whatever. And if we do find a problem, we can restore it fast. That's the resilient side in my mind. Sustainable is a little bit different in my mind, although sustainability, I believe, has become part of resiliency, where we're talking about recyclability. And yes, steel is North America's #1 recycled material. We want to reduce material consumption. Yes, because of its strength and lightweight, we can optimize those to minimize the amount of material we need to put out there. Energy efficient construction. Well, we talked a little bit about construction itself, but that recycled steel conserves energy. And steel energy's use has been reduced by 1/3 since about 1990. Yeah, it takes energy to do it, but they're getting better and better with new and innovative melting systems, and I could name them, but that's all I need to say. And then greenhouse gas emissions, the equivalent carbon that's being produced in the manufacturing and building and that kind of steel, and that's been reduced 45% since 1975 for steel production. And we have, if you want to go to our website, we do have some case studies looking at some steel bridges and some concrete bridges and actually going through the equivalent carbon and the energy use and that kind of thing. And so this is my final slide. I encourage you to subscribe to Dan Snyder. Dan Snyder is on the line. He's been hopefully answering questions in chat and the Q&A. He is the director of the Alliance from the American Iron and Steel Institute, and he's a vice president for construction there. And he sends out a newsletter every Friday at 9:15 Eastern time. And it usually has about 3 items of just general interest or specific interest. And if you read the headlines, if you're interested, you click. If not, you delete it. At least that's what I do. You can find one of our suppliers, whether it's traditional fabricators that you have questions for, or some of our bridge manufacturers that can design and deliver you a bridge. On there, you can get to that E-span or the E-beam, and in 2026, it's going to be the next one for plate girders, which right now we're just calling it E-plate 140, and you can get assistance. And if you're in a region that you think, you know, a 4 hour, a 6 hour, 8 hour webinar that talks about all sorts of different topics on steel bridges, you contact us, and it doesn't cost you anything to bring us out there. We ask you to find a room to host and that kind of thing, and we give webinars. We usually give quite a few of those each year also.